Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good afternoon everyone, and welcome to the lab tutorial. It's a very great pleasure to have Shimon Weitzen from Oxford. Shimon did his PhD at UT Oxford and then spent a few years at the University of Amsterdam, I think. Yes. He's done lots of exciting work in machine learning and artificial intelligence, from theory to building telepresence robots. And he's here today to tell us about multi-objective decision-making, which is something that my wife and daughter said I could really do with learning about. Take it, Shimon.
Thank you, Nick, for the introduction, and thanks also to Katja for the invitation to be here. It's a pleasure to be here today and to have the chance to tell you a little bit about one topic I've been working on for the past few years, which is multi-objective decision-making. Let me start by acknowledging my collaborators. This is Diederik Royers, who was a PhD student of mine when I was still in Amsterdam and is currently a postdoc of mine in Oxford. And that's Frans Oliehoek, who's a longtime collaborator of mine, who's currently at the University of Liverpool. And some of the research I'm going to tell you about today was funded by a grant from the Dutch National Science Foundation. So what I'm hoping to do in this talk is to start by really explicitly motivating multi-objective decision-making, because unlike some other research topics, the motivation is actually not self-evident. So I want to really convince you that it makes sense to reason about multi-objective models and to develop multi-objective algorithms. Then on the basis of that, I'm going to propose a problem taxonomy that sketches a few different kinds of multi-objective problems and describes what the appropriate solution concept is for each of those problems. Then I'll talk about one particular algorithm for solving multi-objective problems that we developed, which is called optimistic linear support. And if I haven't run out of time, I'll talk about an application of that method to a particular multi-objective problem that involves coordinating the behavior of multiple agents. Okay, so let's begin with the motivation. There are many, many real-world problems that are naturally characterized as having multiple objectives. For example, if you need medical treatment, you might want to maximize the chance of being cured, but also minimize the chance of having side effects or dying. If you're trying to build an intelligent system that will coordinate traffic in an urban area, you may want to minimize latency, maximize throughput, respect some kind of fairness principle for all the drivers, minimize environmental impact, and so on. Here's another example. This is a benchmark problem that we use in a lot of our experiments. It's about mining commodities. Imagine you own a mining company. So these red squares are all the mines that you own in the mountains. And in all of the villages, those circles, there are a bunch of workers, and every day you have to decide which workers to send to which mines. And when the workers go to a mine, they can mine a certain amount of gold and a certain amount of silver. And these are two different objectives that you would like to maximize. Okay, so we can see that a lot of problems can be naturally characterized as multi-objective, but that actually doesn't necessarily imply that we need special multi-objective models, that we need new algorithms for dealing with situations that are naturally thought of in a multi-objective way. So I want to try to convince you that, in fact, we do need those models. I want to start with something called Sutton's reward hypothesis. So some people actually don't believe that we need multi-objective models. Some people explicitly argue against having any kind of multi-objective models or algorithms. And one of these people is Rich Sutton, who quite literally wrote the book on reinforcement learning. So he's formulated what he calls the reward hypothesis, which says all of what we mean by goals and purposes can be well thought of as maximization of the expected value of the cumulative sum of a received scalar signal, the reward. So here I've just tried to sort of formalize what Sutton is saying in the reward hypothesis. So we have here this capital Pi. This is a set of policies, which we can just think of as a set of possible solutions to our optimization problem. And this function V is a value function. It maps each one of these policies to some scalar value that says how good that policy is. And as Sutton is saying, the value of any given policy can be thought of as the expectation of some summation of some reward signal. And to solve the problem, we want to find the best policy, and the best policy is the one which will maximize this scalar reward.
I'm a bit surprised it's not a weighted sum or something. So over V, it doesn't matter.
Weighted over what?
Oh, I see. Well, like the gold and the silver, right? So you're saying you're going to kind of say gold is worth this much, silver is worth that much, and you sort of do a weighted sum, and that's your V, is that right?
Yeah, so that's a scalarization of the problem, which I'll talk about in detail in a couple slides. So I think that will become very clear. So, but what Sutton is starting from the position that we don't have these multiple objectives. He's saying, okay, every policy can be mapped to some scalar value. So we don't have multiple objectives yet. So there are several things that I could object to in the reward hypothesis. I could say, hey, sometimes I might want to be risk sensitive and not maximize expected value. Or I might say, I might have a problem where the rewards don't decompose as a sum, a non-additive problem. But for now, I'm just going to focus on this one aspect of the reward hypothesis, which is that the assertion that this signal is scalar. Okay, so in order to motivate multi-objective methods, we're going to have to argue against the reward hypothesis. And there are two parts to this argument, what I call the weak argument and the strong argument. Now, the weak argument is the argument that I was already implicitly making at the beginning of the talk when I showed you these examples. The weak argument says simply, there are many real-world problems that can be naturally thought as having multiple objectives. So rather than mapping these policies to scalars, we map them to vectors. So n here is then the number of objectives. And so every policy has some value in each objective. And I'm using bold here to indicate vectors. So V is now a vector. The reason this is called the weak argument is because the devil's advocate could come along and say, hey, why don't we just scalarize this multi-objective problem? And what do we mean by scalarize? We use a scalarization function that projects the multi-objective value onto a scalar. So here we have on the left-hand side, this V is not bold, so we have again a scalar value. And this scalar value is determined according to some weights, which are the weights of the scalarization function that converted the multi-objective value back to a scalar one. So f is our scalarization function. It's a function of the multi-objective value and some weights that parameterize the function. So the most intuitive case, which I will talk about a lot today, is the linear case, in which case the scalarization function simply computes an inner product between the multi-objective value and some weight vector. So what this weight vector is doing is specifying an a priori prioritization of the objectives. And the devil's advocate objection to the weak argument is to say, if I just perform this scalarization, I have a single objective problem again, and I can just apply all my single objective methods off the shelf without having to do any new research, without having to develop any new methods. So to respond to the devil advocate's objection, we need to make a strong argument. So the weak argument is necessary but not sufficient. And the strong argument says, this a priori scalarization is sometimes impossible, infeasible, or undesirable. And in such cases, it's not sufficient to take a single objective method which will give us one policy as a solution. Instead, what we need to do is produce a coverage set of all undominated solutions, all solutions that could possibly be optimal when later we perform the scalarization that now we are unable or unwilling to do. Okay, so why would we be unable or unwilling to scalarize a priori? There are three different scenarios that sort of capture the reasons. The first scenario is what we call the unknown weight scenario. So in this scenario, we simply do not know the weights of the scalarization function at the moment at which we have to do the planning, at the moment at which we have to select, do all the computational work to figure out what policies are good. So the idea here is that the weights will be known later at the moment at which we have to execute the policy, but they're not known at the moment at which we have to do the planning. So that's what this figure sort of illustrates. We have a multi-objective problem. We feed it as input to our planning algorithm, which produces not just a single answer, but a coverage set, the set of all possible undominated solutions. Then later, the weights become revealed to us, and in the selection phase, we use those weights to scalarize the problem and select a single policy from this coverage set, which we then execute. So
this visual planning algorithm is too slow.
Yeah. So you can think of it that way. So at the moment at which we find out the weights, it's too late to then do all the planning.
Too late in what sense, right? If the planning algorithm only took half a second to execute, you might think, boom, I just run the planning algorithm with the old single objective thing.
Yeah, that's absolutely what you should do.
So the assumption here is it takes ages to do stage one, and you want fast stage two.
Yeah, it takes ages in comparison to the amount of time between when the weights are revealed and when you have to act.
Okay.
And Richard is thinking here there might be some analogy where you have to dig holes for the mines or something. Can you make something where it really, really is too slow?
Yeah. So figuring out the best way to send all the workers to the different mines may be very computationally expensive. So that's a planning problem which may require a lot of resources, and doing that at the last minute when the weights are revealed may not be feasible. So think of the price of gold and silver changing throughout time, just according to the market. The later that you make the decision about when to how to prioritize gold and silver, the later you make that decision, the better off you'll be, because the closer the decision will be to what the market price will actually be when you sell gold and silver.
But Andrew was suggesting, weren't you, that you maybe once you got the coverage set, you could maybe build some roads from some of the villages to some of the mines, because you could see they were likely to be useful ones.
Oh, sure, yeah. Yeah, so the coverage set might have other uses besides just selecting a policy to execute. Yes. Yes, I agree. Okay, so another scenario is what we call decision support scenario. In this scenario, it's not so much that the weights are unknown, it's that the weights can't really ever be quantified in the first place. So the weights, if they exist only implicitly inside the brain of some user. So the user cannot really meaningfully quantify the weights, but the user can express preferences. So for example, in this medical treatment scenario, if I said, okay, how much more important is it to you to avoid side effects than to be cured of the disease? Is it 2 times as important, 3 times as important, 2.4 times? It's hard to meaningfully quantify that distinction. But if I say, okay, here's one treatment option with a certain profile of risks, and here's another treatment option with a different profile of risks, you can probably figure out which one is right for you. So in the decision support scenario, everything proceeds exactly as in the unknown weights scenario. We have this multi-objective decision problem, we compute this coverage set, but then in the selection phase, instead of the weights being revealed, we just show the coverage set to the user, and the user selects whichever policy he wants according to his idiosyncratic preferences, which might implicitly correspond to weights that are somewhere in the user's brain.
Can I ask something? So if you say you give me these options, for example, and they are like 2 vectors of several things, and then you say, okay, and you just said you can figure out which one you would prefer from the 2. That means that in your brain you do have a ranking function, right? So it might not be a linear function of the weights of the individual one, but there is a ranking function.
Yeah, that's what I mean when I say the weights may exist implicitly in the user's brain. Like implicitly the user is using a scalarization function which has some weights. We did.
So the objection in all of the slides that I've seen so far is not so much to the existence of scalarization, but to the scalarization is a linear combination of other things. That's the objection I see, no?
No, so there are 2 issues. One issue is the scalarization function linear or not? In both of those cases, multi-objective reasoning can make sense, but the nature of that multi-objective reasoning will be different. And I'll talk more about that later. But do you want to be multi-objective at all? I think depends on whether you meet any of these 3 criteria. So only in unknown weight scenario do we say the weights actually, we cannot use the weights when we have to plan. In this one, when it's infeasible, that's decision support. In principle, these weights do exist, and it's not they're as known during execution as they are during planning. But it's just hard to really put a number on them. How are you going to extract that number from the user's brain? It's easier to just show them options and have them choose those options than to ask them to pick weights of a scalarization function. And then the third scenario where it's just infeasible to scalarize is what we call the known weight scenario. I'm not really going to talk about this today, but I just want to mention it for completeness. There's some scenarios where you actually do know the weights at the planning phase, and you could scalarize, but that scalarization yields a problem which is actually much harder to solve. And there are some reasons for that which I won't really go into, but just for example, if you scalarize according to a nonlinear function, then you might no longer have additive properties. So you may no longer be able to decompose this value as a sum, the way Sutton claimed in the reward hypothesis, in which case whole families of methods based on things like the Bellman equation would not be applicable. So it may actually be easier to just solve the problem in a multi-objective way, even though you could scalarize. So those are the 3 scenarios. So this is a summary of the motivation. Basically, multi-objective methods are useful because many problems are naturally characterized by multiple objectives, that's the weak argument, and cannot be easily scalarized a priori, that's a strong argument. Okay, so hopefully I've convinced you that at least in some cases it makes sense to think in this multi-objective way. So now what I'm going to do is propose a taxonomy of multi-objective problems and talk about what constitutes a solution to each of those problems. Okay, so if you look at the multi-objective literature, there are kind of 2 different approaches to coming up with solution concepts. The first one is what I call the axiomatic approach. And in this approach, we just define the optimal solution set to be the Pareto front. And the Pareto front is a concept that's probably familiar to most of you. In the other approach, which we call the utility-based approach, we try to actually reason from more basic principles about what the solution concept should be. So the reasoning is as follows. During this execution phase, at the end of the day, we can only actually execute one policy. So if we select that policy in a rational way, then that policy will be optimal with respect to some scalar utility. It will be the policy which maximizes scalar utility according to some weighting of a scalarization function. And this W may be hidden or implicit because it might be in the user's brain. But the idea is that it exists in some Platonic sense out there.
But it will be linear.
It might or might not be linear.
Okay.
I'm not committing to the linear assumption yet.
Okay.
Now I'm speaking generally. So these are just, W just parameterizes some arbitrary scalarization function, F. Okay. So given that the policy that we select is optimal with respect to some W, then the goal in the planning phase is to find a set of policies that contain an optimal solution for each possible W. So we don't know what W is when we have to plan, so we want to cover all our bases by having a policy that's optimal for all W. So if W is unknown, then in general, the size of this set will be greater than 1. So what we want is a set that doesn't contain policies that are suboptimal for all W, because even though we don't know W yet, we do know that we don't want those policies. We can already rule them out. So multi-objective planning can be thought of as a pruning process. We prune away the policies that we know won't be useful, even though we don't know W yet. Okay, so what exactly does this set consist of? That we can deduce from properties of the optimal solution set and this scalarization function. So for example, if we say the scalarization function is linear, then we'll end up with a different solution set than if it's nonlinear. So that's what the taxonomy will illustrate. So let's start with some definitions. Let's formalize this idea that we want to prune away the policies that will never be useful. Okay, so an undominated set is a subset of all the possible policies for which there exists some W for which the scalarized value is maximal. So it's a set of all policies such that it's in one of the possible policies, and there exists some weight such that for all other policies pi prime, the scalarized value with respect to that weight of the policy pi is greater than or equal to that of pi prime. So there exists some W that sort of justifies the existence of this policy, because at that W, that policy is optimal. Okay, but it turns out this is slightly overkill, because this undominated set can include policies that we don't actually need to keep. So what we actually are interested in is the coverage set. The coverage set is a subset of the undominated set, such that for every W, there exists a policy in the coverage set that maximizes the scalarized value. So it's a subset of the undominated set, and for every weight, we have some policy that's in the coverage set and which is optimal for that weight. Okay, so here's a simple example that just illustrates the distinction between the undominated set and the coverage set. So here we have, now normally this weight vector is going to have continuous values, so we're going to have a continuous weight space. But in this very simple example, we just have a binary weight space. There's just two possible values that W could take on. Now, I'm not saying there are only two objectives. I'm not saying anything about how many objectives there are. I'm just saying this multi-objective problem is scalarized with respect to a scalarization function that's parameterized by W, and W is binary. Okay, so there are two possible scalarizations. And now we have 4 different policies, and for each policy we can see what the value of that policy, what the scalarized value of that policy is under each of the 2 possible scalarizations. Okay, so now we can easily see that the undominated set in this example is policies 1, 2, and 3. Because for each of these policies, there's one scalarization for which that policy is optimal, right? However, we can construct a coverage set that uses only 2 of those 3 policies, either 1 and 2 or 2 and 3. Because there's only 2 possible scalarizations, and we can cover both of them using only 2 policies. Okay, so what we're trying to find then is the coverage set. Once we found this coverage set, then in the execution phase, we're going to use that coverage set to figure out which policy to actually execute. In the unknown weight scenario, the weights are revealed to us, and then we can just select the maximizing policy by performing this argmax. We just iterate over the policies in our coverage set and find the one that has the largest value scalarized according to the weights which are now known.
Do you assume that pi is finite in order to compute the coverage set?
No, it does not need to be finite. So I'm going to discuss scenarios where we consider both deterministic policies or stochastic policies, and then if it's stochastic policies, then it's clearly there's an infinite number of possible policies.
What's the optimal policy, only I know where your cursor is now? If you just replace pi in CS of pi with pi in all policies, then that's the original problem spec.
Absolutely, yeah.
So you're kind of relying on CS being rather small compared to the whole policy space.
Well, it just has to be smaller. That's the point, is we have like a partial planning process. We want to do as much as we can before we know the weights, and then afterwards we'll do whatever we couldn't do beforehand. Right. So the more policies we prune away, the more work we save during the execution phase.
So you're hoping to save a lot of work. Right?
Absolutely, yeah, yeah.
So you're hoping that CS is really rather small.
Yeah, definitely. The smaller the better. And of course, you can construct worst case scenarios where the coverage set contains every possible policy, and then the multi-objective planning offers no leverage at all. Okay, so in decision support, then we just show the coverage set to the user, and the user selects a policy. Okay. So here's the problem taxonomy. We're going to look at two different dimensions. So one is this scalarization function linear, or does it obey only a weaker assumption that's monotonically increasing? And do we insist upon having deterministic policies, or do we allow stochastic policies? So for each of these four scenarios, I'm going to describe what the appropriate solution concept is. So let's start with the top left. Let's consider for now only deterministic policies, and let's assume the scalarization function is linear. So as I already mentioned, if the scalarization function is linear, it just computes the inner product between some weight vector and the multi-objective value, in which case each weight is quantifying the importance of one of the objectives. For mathematical convenience, we typically assume that this is actually a convex combination, so that all the weights are greater than or equal to 0 and that they sum to 1. Linear scalarization functions occur a lot in practice, and they're very intuitive, particularly in any situation where utility at the end of the day translates to money. Then a linear scalarization function makes a lot of sense, because those weights just correspond to the cost per unit of each objective. So for example, the cost of gold and silver would be then the weights of the two objectives. Okay, so if we assume a linear scalarization function, then the analog to this undominated set is the convex hull. So the convex hull is the subset of policies for which there exists a W that maximizes the linear scalarized value. So this definition here is exactly the same as the definition I showed you earlier for the undominated set, except now I've explicitly computed the scalarized value using this inner product, because the scalarization function is linear. Right? And the analog to the coverage set is the convex coverage set, which again, this is the same definition as before, but now we compare policies using this inner product. Okay. So we can visualize this in two ways. Sorry, was there a question? Oh. We can visualize this in two ways by looking at objective space and weight space. These figures are very important for understanding everything that comes later, so I will do my best to make this clear. So on the left-hand side, we have objective space. So what we have a problem here with two objectives, objective 0 and objective 1. And each of these points corresponds to a different policy. And the location of that point tells you the multi-objective value of that point. So here we have a point that is a better example. This point gets a value of 2 in objective 0 and a value of 1 in objective 1. Okay. So the convex hull consists of the red and blue points here together. And I've drawn this line connecting them just to give some intuition as to why this is called the convex hull. And however, the blue point is on the convex hull, but not in the convex coverage set. And we can see why it's not in the convex coverage set by taking a look at weight space. So in weight space, on the x-axis here, we have the value of one of the weights. So remember, because we have two objectives, so the scalarized value is this, this inner product. And because we assumed that it was a convex combination, we know that W0 is equal to 1 minus W1. So I can completely describe the weight space in this simple example by just specifying the value of W1. Okay? Now, each of these points in objective space corresponds to a vector in weight space, because each of those points has a multi-objective value. So that's its value at the endpoints. This is the value if I only care about objective 1. This is the value if I only care about objective 0. And the scalarized value will change according to this line as I change where I am in weight space. And because the scalarization function is linear, it changes in a linear way, yielding these vectors. Okay, so what is the convex coverage set? The convex coverage set are all the policies whose vectors contribute to this undominated upper surface. And if you have any experience with planning and partially observable Markov decision processes, this will be extremely familiar to you. Okay, now the blue line does participate in that upper surface, but we can still represent that whole upper surface without that blue line, because it only contributes at this one point, at which other policies are also optimal. So this illustrates why this blue point is in the convex hull, but not in the convex covered set. Okay, so that was the top left corner. Because we have a linear scalarization function, and for now we're considering only deterministic policies, our solution concept consists of a convex covered set of deterministic policies.
So that you, 2 slides ago, you gave us a definition of the covering set, right? And in this last slide, the thing you didn't tell us, but I think you're saying is that those guys at the top are kind of small subset of the points that are going to characterize you're giving us some reason to believe that the set is small. Right. 2 slides ago, you just gave us a definition, which could have been the whole set for all we knew.
It can, in the worst case, be the whole set, yes.
Okay.
Yes.
But through these pictures, you're encouraging us to believe that for this linear thing, you could kind of see that there's likely to be so the ones at the top, the ones that aren't grayed out. Yeah.
So
there's a reasonably small subset.
In practice, that's absolutely the case. But yeah, I mean, you can easily construct an example where each of these vectors participates in this upper surface, and then you just can't do anything.
Yes, okay.
Yeah.
But the idea is roughly that the perimeter of a set is smaller than the set itself.
Yeah, exactly. Yeah.
There you go. That's what I was struggling to say. Yeah, good.
Yeah. Thank you for helping me to answer that question. Okay, so what if I'm not prepared to assume the scalarization function is linear? Then we can make a weaker assumption, which is that the scalarization function is monotonically increasing. So a scalarization function is monotonically increasing if changing a policy such that its value increases in one or more objectives without decreasing in any other objectives also increases the scalarized value. So in other words, all else being equal, I'd rather have more of any given objective. And I would argue this is a minimal assumption, because if we don't satisfy this assumption, then we don't have the basic notion that an objective is something that's good. Meeting an objective is something that's good. The value is no longer inherently positive. So I think this is a minimal assumption. If we make this minimal assumption, then we know we can ignore policies that are Pareto dominated. And a Pareto dominated policy, so a policy pi Pareto dominates another policy pi prime if its value is at least as high in all objectives and strictly higher in at least one objective. And this is a concept that's probably familiar to many of you. Now, policy is Pareto optimal if no policy Pareto dominates it. Okay, so the analog to the undominated set, in the case where we have these monotonically increasing scalarization functions that are not necessarily linear, is the Pareto front. And the Pareto front is just a set of all policies that are not Pareto dominated. And again, this might be slightly overkill, so we can define the Pareto coverage set. It's a subset of the Pareto front, such that for every policy pi prime, it contains a policy that either dominates pi prime or has equal value to it. Okay, so let's go back to our visualization. So it's exactly the same visualization as before, but now I've added a new point here, this black point. Or sorry, I've changed that point from gray to black. Because this point, while not in the convex hull, it is on the Pareto front. We can see that it's in the Pareto front by looking at the region that's to the up and right of it. It's empty. There are no dots there. So there's no policy that Pareto dominates this policy, therefore it's Pareto optimal and in the Pareto front. And if we look at weight space, so this black line corresponds to this black point, it's on the Pareto front. We can see that because even though this black line doesn't contribute to this undominated upper surface, there is no single other line which is always above it. So Pareto dominance is a pairwise notion of dominance. That means you need to find a single other policy which dominates it, and that's not possible for this black line. But it is dominated by a combination of other lines, and that's why it's not on the convex hull. Okay. Right. So what we've concluded then for this bottom left corner is that if our scalarization function is only monotonically increasing, we want, instead of this convex coverage set, we want this Pareto coverage set. Okay, so let's now relax the assumption that we have deterministic policies, and let's consider stochastic policies. So what is the deal with deterministic versus stochastic policies in multi-objective decision-making? So in most settings, stochastic policies are fine. However, there are some settings...
What is a stochastic policy?
Sorry. Okay, a stochastic policy is one that involves some randomness, that selects actions probabilistically.
Okay, to spin a coin and decide what to do.
Yeah, exactly.
Shall I take this drug or that drug? Flip a coin.
Exactly. And that you're hitting on exactly why they might not be desirable in some settings. So If you're making a control policy for a robot, you might not mind if its behavior is stochastic. But if you go to the doctor and the doctor says, I've got a great treatment plan for you, the first thing we're going to do is flip a coin, you might not feel comfortable with that. And there might even be ethical reasons why the doctor shouldn't propose such a solution. So you might or might not agree with that. Maybe you would be fine with flipping the coin yourself. But the point is there are some settings in which at least some people don't want stochastic policies. Now, in many settings, from a decision-making perspective, requiring deterministic policies is not a restrictive assumption. So for example, in the Markov decision process, it's well known that there always exists at least one deterministic optimal policy. So you can restrict your attention to deterministic policies without sacrificing value. And for multi-objective extensions of such settings, so for example, a multi-objective Markov decision process, if I use a linear scalarization function, then I have a nice result that I can again restrict my attention to deterministic policies. So the result says that the convex coverage set applied to the space of deterministic policies is the same as the convex coverage set applied to the set of all policies. So looking at only deterministic policies is a lossless restriction.
So the question, just before you head on, just to make sure that I'm kind of following this. So the way I'm thinking about it might actually really occur in medical treatment because the doctor might say to you, there's this medical trial that I can put you in for, which sounds promising, but if you go for it, there's a 50% chance you'll get put in the control group. Right? So in that case, the doctor might indeed toss a coin, which would be whether you get put in the control group for the medical trial or the real treatment group for the medical trial. But you might still, if there's no good alternative, opt to go for the medical trial, right?
So the key issue there is whether we consider that stochasticity part of the environment or part of the policy. So is that a coin flip which is under your control? I mean, let me try to rephrase that. Do you get to choose to flip the coin? Obviously, you don't get to choose the outcome of the coin. Do you get to choose to flip the coin, or is that something that happens externally to your policy? So even if we restrict our attention to deterministic policies, that deterministic policy may be applied in a stochastic world. The world may respond stochastically to our deterministic actions. Like, I decided to enter the trial, and then the world flipped a coin to say whether I was lucky or not. But the point is, in some settings, so here I said in many settings deterministic policies are not restrictive, but there are settings in which it is, in which case, if you have stochasticity under your control, you can choose to flip coins, then not doing so will actually hurt you. There are some such settings. Okay, so here I'm saying go ahead.
I was just wondering if those are generally adversarial settings or if there's some other...
The two main sources of benefit to stochasticity are adversarial settings. If the other agent is against you, then you want an element of surprise, so like in a game theoretic setting. And the other one is partial observability. So if you don't reason about partial observability in an optimal way, then having stochastic behavior can help you sort of prevent getting stuck in a rut. Okay, so but in the settings where deterministic policies are not restrictive, then we can extend, then in the multi-objective extensions to those problems, it's also not restrictive to look at deterministic policies if we have a linear scalarization function. Okay, so what that means is, when we have stochastic policies, and the linear scalarization function, we can still have as a solution concept a convex coverage set of deterministic policies. Because we know we can just ignore the stochastic policies and there's no loss there. Okay, what about if we have stochastic policies and a monotonically increasing scalarization function? So because we have a nonlinear scalarization function, stochastic policies may actually be preferable. So what can we do about that? We can reason about what we call mixture policies. And what is a mixture policy? It just assigns, it takes a set of n deterministic policies and assigns a probability to each one. And then when the policy is executed, we just sample from the resulting probability distribution and execute the corresponding deterministic policy. So this mixture policy has value that's a convex combination of the value of the constituent policies. So, right. So if we look at our figure again, this red line that connects the dots on the convex hull is no longer just for illustrative purposes. This line now corresponds to the value of all the different mixture policies that I can construct from the deterministic policies in my convex coverage set. Okay, so what are we going to do now that we have a nonlinear scalarization function and we're allowed to consider stochastic policies? It turns out that a Pareto coverage set, that's what we want for our nonlinear scalarization function, can be constructed by mixing policies on the convex coverage set of deterministic policies. And you can see that by saying, okay, if we just construct this convex coverage set, what are we missing? This convex coverage set of deterministic policies, what are we missing? We're missing the stuff that's in the Pareto coverage set, but not in the convex coverage set, like this black guy, this black dot. Right? This guy was on the Pareto front, but not on the convex hull. And if you look, you can see this point is clearly dominated by points on this red line that are in this rectangle. So we know we can find mixture policies here that dominate this thing that we left out. So we can get away with leaving it out. So even though we have a nonlinear scalarization function, all we need to compute is this convex coverage set of deterministic policies. So if we look back at our taxonomy, we see something a little bit surprising. 3 of the 4 boxes here have the same solution concept, the convex coverage set of deterministic policies. Even if we aren't willing to assume that our scalarization function is linear, we can still get away with this convex coverage set of deterministic policies unless we have this one combination. If we insist upon deterministic policies and we have a scalarization function that we don't know to be linear, then we need to actually compute this Pareto coverage set. In all other cases, the convex coverage set is enough. So this is kind of a take-home message of the solution concepts. Unless the scalarization function is both nonlinear and we require deterministic policies, the convex coverage set of deterministic policies suffices.
But computing that from the convex hull is not too difficult computationally, right? Because you just, it's exactly what you take like neighboring points and you take rectangles and then you see if that intersects with an existing policy and then you're done.
Sorry, you mean to find something, to find a mixture policy that, yeah, exactly.
So that's okay, that's cheap, probably.
Yes. Yes.
Mixture policies might be okay if you're going to run things repeatedly. Like the villagers are going to dig in the mines, right? Once you sent them out, they've gone, right? So if you're doing that every day for a year, then you could flip coins, right? But if you're just doing it for one day, then you have to choose make one choice, don't you?
So a detail that I didn't really go into is that when we move from deterministic to stochastic policies, we have to think a little bit more about how we define optimality. And so here we're defining optimality as maximizing expected value.
Okay, so now you are implicitly iterating.
Yeah, and in some cases, so another objection, and could give a whole other talk about this, another objection to the reward hypothesis is sometimes we might not care about expected value. We might want to be risk sensitive, or we might say we have a process which isn't repeated many times, so the expectation is not of interest. All of those are valid objections, but here we're assuming we care about the expected value of the stochastic policy. Okay, so how am I doing on time? I think I'll be okay. Okay, so that was sort of a whirlwind tour of multi-objective decision making. Now what I'm going to do is tell you a little bit about a specific algorithm that we've developed, and it probably won't be a surprise to you at this point that this algorithm computes the convex coverage set of deterministic policies, because the point of the taxonomy was to motivate why this is really the thing that we should be computing in most situations. Okay, so let me try to, before I tell you the details of the algorithm, let me try to put it in context a little bit. There's kind of 2 families of multi-objective methods, what we call inner loop and outer loop methods. So this box here is a sort of simple illustration of how a single objective method works. So the single objective decision-making method, it's trying to maximize value. So somewhere in this method, there's going to be some kind of maximization performed to find the best policy. So what an inner loop method does is it takes that single objective method and replaces this max operator with some other operator that's like a multi-objective analog to maximization. And basically that multi-objective analog is pruning. So you can think of maximization as an extreme form of pruning. You prune away everything except the one best one. And here in the multi-objective setting, we prune away only the things that we know to be suboptimal before we know the weights. So pruning is the multi-objective analog to maximization. So we take some single objective method, we get rid of that max, we do some pruning. Instead, we have a multi-objective method. We call this an inner loop method because the multi-objectiveness of the method is deep inside some inner loop of the method. Okay, what we can also do is take an outer loop approach, where we say, okay, we just take our original single objective method and we don't alter it at all, but we just put a wrapper around it. We just call it as a subroutine inside some larger method, which figures out in a clever way a series of single objective methods to solve, such that the solutions to those single objective problems constitute the solution to the multi-objective problem. So we sort of incrementally construct the convex coverage set by solving a series of single objective problems. So optimistic linear support is a method that we've developed, which is of this latter form. So it's an outer loop method. And this is based on, it's an adaptation and improvement to a method called linear support that was developed by Chang in the 80s for solving partially observable Markov decision processes. And you might remember I mentioned before that this undominated upper surface, this is a concept which comes up in POMDPs all the time, and so there's a close relationship between POMDP methods and multi-objective methods, so we've sort of leveraging ideas from that literature. But linear support was never a practical method for POMDPs, but it turns out to be a very good starting point for multi-objective methods. Okay, so what does optimistic linear support do? It solves scalarized instances for specific weights. So we're going to select, we don't know what the true W is, but we're going to select a bunch of different W's, and for each one, we're going to solve the corresponding scalarized problem. And we're going to use those solutions to construct the convex coverage set. And this coverage set is going to cover this whole continuous weight space, but it's going to terminate after checking only a finite number of weights. And it's going to, if we wanted to, compute the exact convex coverage set. Okay, so this the next series of slides illustrates how optimistic linear support works. So we start at the extrema of the weight space. We say, okay, suppose I put all the weight on one objective. That yields a scalarized single objective problem where I only care about that objective. Let me feed that to my single objective solver. It will give me a policy which is optimal for that weight. Okay? So this is the best possible value you can get for this weight. But that policy that it returned has a value for all weights, and that's what's indicated by this vector. So this vector is all the different possible scalarized values of the policy we received, which is optimal for the weight at which we perform the scalarization.
And our hypothesis is that we can know what the value of that policy is for all weights cheaply. That evaluation is cheap, is it?
Yeah. So what I need is a single objective method which returns not just the policy that's optimal for that weight, but returns the multi-objective value of that policy. So it tells me what is the value of this optimal policy with respect to each objective. If I know that, then computing this vector is trivial, because it's just computing that inner product for whatever weight vector you want. But I do need to know the multi-objective value. Okay. So now I'm going to do the same thing for the other extremum. That yields another vector. And then where these two vectors meet, this is what's called a corner point. And Chang had a result which said that the place at which the current solution can be maximally improved will always be at a corner point. So we're going to select this corner point, and we're going to scalarize according to that weight. We're going to feed that to our single objective solver. We get yet another vector. And adding that vector creates two more corner points. We're going to test those corner points. And when we test those corner points, we won't get any new vectors. When we test those corner points, we'll find out that, oh, the vectors we already had were already optimal for those corner weights. So now we're done. No new corner weights were created because no new vectors were added. So we're done. We've tested only 5 points, and we have now this undominated upper surface corresponds to the convex coverage set, gives a policy that's optimal for any point in this continuous weight space.
What are you saying? In that sense, it just happened that for this example, it terminated after these two.
In this example, it was 5, but it will always terminate after a finite number because the convex coverage set is of finite size. Okay.
For a finite size pi.
Yes. Yes. That's correct. Okay, so the reason we call this optimistic linear support is because we take all the corner weights that we've generated but not yet tested, and we put them in a priority queue. And the next corner weight we process is always at the head of this priority queue. And the priority is based on what we call maximum possible improvement. So let's take a look at this point here. Let's take a look at this corner point. So we haven't tested this corner point yet, so we don't know what the vector corresponding to the optimal policy for this weight, we don't know what it's going to look like. But we can put an upper bound on it. We can say, okay, whatever this vector is, it had better obey the constraints imposed by the points we've already tested. So that's what's shown by this dotted line. This dotted line is the most optimistic scenario for what this unknown vector could look like. So this vector has to pass under the points that we've already tested at the weights at which we tested them, right? Because when we tested this weight, we found the optimal policy for that weight. So it cannot be possible that then when we're testing another weight, we get a policy which is better according to that previous weight. So each of the weights we've already tested generates a constraint, and we can compute this, this dotted line, this optimistic vector, by solving a linear program. And the difference between the value of this vector and the corner point at the given weight, that's this delta. This is the maximum possible improvement. This is the most that our solution could improve at the current weight by processing that weight, by solving that weight. So that's our priority, is this delta. And the nice thing about using this maximum possible improvement as the priority is it naturally gives us a way to generate approximate solutions and turn our algorithm into an anytime algorithm. So I can, for example, say, I'll settle not for the convex coverage set, but for an epsilon convex coverage set. And then how do I know when I have an epsilon convex coverage set? I just stop when the thing at the head of the priority queue has a delta less than epsilon. Because I know processing that corner weight cannot yield an improvement greater than epsilon. So I'm already within epsilon of optimal. And everything else in the queue is going to be even smaller. Or I can just run until time runs out, and then I can say, okay, how good is the solution that I had? I know that it's an epsilon CCS, where epsilon is the delta corresponding to whatever's at the head of the priority queue. Yeah, question?
So, yes, at least from the picture, it looks like a slightly different criterion would be to look at the volume, the maximal volume that you can remove out of your optimization problem rather than the vertical distance that you may want to get. Now, does it make sense? Or? If you want to converge as soon as possible, the more surface you destroy.
Yeah, so this volume corresponds to the total amount of suboptimality of the current solution. The maximum possible improvement corresponds to the suboptimality at this point.
So that would be, those two will be the same in effect.
They're not the same. They're definitely not the same. I think the priority queue would order them differently if you use that criterion. Would that be better or worse? I don't know off the top of my head. I would need to think about that. That's an interesting idea. Maybe we can talk about that offline. Okay. Right, so what we can also do is say, maybe we have a problem which is too difficult, for which it is too difficult to solve even a single scalarized instance. So I'm solving multi-objective Markov decision processes. The Markov decision process has a million states. I can't afford to come up with an optimal solution to even one scalarized instance. So what I want instead is to use an approximate solver instead. Suppose that approximate solver has bounded error. So I feed my scalarized instance to that single objective solver. It gives me an epsilon optimal solution. I can just fold that epsilon into my decision making at the multi-objective level. So when I compute this maximum possible improvement, I consider not just the distance between the vector, between the current point and this optimistic vector, but I raise the roof by an amount epsilon, corresponding to the fact that the values I've computed may actually underestimate the true optimal value by an amount epsilon. And I know it won't be more than epsilon because I'm using an epsilon optimal single objective solver. Okay. So that's optimistic linear support. The main advantages of it are that I can apply this to any multi-objective problems. It's not really an algorithm. It's a generic framework that can be applied to any multi-objective problem because it's really just a wrapper around the single objective method. So I can apply it to any multi-objective problem for which I have a suitable single objective solver. What is a suitable single objective solver? Well, this was already discussed in answer to a question. So basically, it's a solver which gives me not just the optimal policy, but which tells me the multi-objective value of that policy so that I can reason about those vectors. This is not a huge constraint in practice. Another nice property is that it inherits the quality guarantees of the subroutine. So as I mentioned before, if I have this epsilon optimal single objective method, I can take that bound on the single objective method and push it through the multi-objective method to get a multi-objective method with bounded error. For small and medium numbers of objectives, this is way faster than an outer loop approach. For large numbers of objectives, the number of corner points that are generated becomes prohibitive, and inner loop methods are faster. Now, there are certainly real-world problems where you might want to model them as having thousands of objectives. Like that traffic problem, you might want to say every driver is an objective, in which case you would definitely not want to use OLS or any outer loop approach. But most of the problems you come across in the literature, and I think many problems in practice, actually have only a few, 2, 3, 4 objectives. This is sort of natural resolution at which people think about multi-objective problems. And for that whole family, I think an outer loop approach like OLS is the way to go. Okay, so the last part of my talk is about an application of OLS to a particular problem. I think I'm going to skip some details here because is that including questions? Sorry?
I was allowed for some questions.
Okay. I'll try to wrap up in 5 minutes and then you can ask as many questions as you like. So just applying OLS to this particular problem of multi-objective coordination. Okay, so what is multi-objective coordination? We have a bunch of agents. They're on the same team, but they need to figure out how to coordinate their behavior so as to maximize their shared payoff. So we have n agents, and we have a joint action space, so each agent can select some action. And we assume that this utility that they're trying to maximize is the sum of some local payoffs. So the total payoff of the team is a sum of some local payoffs, where each local payoff depends on the action of only a subset of the agents. So in other words, there's a graphical structure here that can be exploited. So this can be captured in, for example, a factor graph. Here we have 3 agents, and we have 2 payoff functions. Say this payoff function depends only on agents 1 and 2. This one depends on agents 2 and 3. Okay? So as you may or may not know, there are many algorithms that have been developed to solve this kind of problem. These methods were originally developed in a probabilistic setting, but they can be applied to this optimization setting very easily. One of them is called variable elimination. The main idea is that for each agent, we're going to compute the value of its best response to all of the local joint actions of its neighbors. And in doing so, we can construct a new local payoff function that eliminates the agent from the graph. This gives us a computational complexity only in what's called the induced width of the graph, rather than in n. So rather than having to iterate over this exponentially large action space, we can much faster find the maximizing joint action. Okay, if we take this problem to a multi-objective setting, we have exactly the same thing as before, but now these payoff vectors are vector valued. So you have a total team payoff that's a vector, multi-objective payoff, and it's a sum of the multi-objective local payoff functions. So here we have these local payoff functions, and if you know anything about game theory, this might look to you like a normal form game, but it's actually a little bit different. So it's not the case that 4 is the payoff for one agent and 1 is the payoff for the other agent, because they're on the same team. This is the shared but multi-objective payoff of the team. So they have the same interests in mind, but those interests are multi-objective, and so this is the value in one objective and the value in the other objective. Okay. So what we could do is we could take an inner loop approach. We could say we take this variable elimination algorithm that I very quickly sketched. We could replace maximization with a pruning operation. So we've actually done this. So some people did this before us to compute Pareto coverage sets. This is the work of Roland and LaRosa. We took that work further for computing convex coverage sets. This is an inner loop approach. What we can also do is take an outer loop approach. So we can just take this optimistic linear support framework I described earlier, just stick variable elimination in as the single objective solver, and we're done. This is an algorithm we call variable elimination linear support. So this graph shows some results that we obtained using these methods. So on the left-hand side, we have some randomly generated problems. So we have an algorithm for generating random graphs, and then we solve those graphs. And then this is, on the right-hand side, we have the commodities mining problem that I showed you at the beginning. This is a 2-objective problem. Okay, so on the x-axis, we have number of agents, and on the y-axis, we have the runtime of the algorithm. And notice the log scale here on the y-axis. So the first thing that these results show is that this red line, CMove, although it starts out slower than this brown line, which is PMove, so that's computing the Pareto coverage set, even though it starts out slower, its growth is a lot more gradual. So as we get to larger numbers of agents, computing the convex coverage set is key to keeping the problem scalable, to keeping it tractable. And what we can also see is that if we take an inner loop approach using vels, that's this black line, we get an algorithm that runs much faster. So this is like an order of magnitude, or almost an order of magnitude due to the log scale. And what we also see is that if we tolerate even a very small epsilon, that also yields a big speed up. So by by computing the convex coverage set, taking an outer loop approach, and tolerating a small epsilon, we can greatly improve the runtime of this algorithm, of solving these multi-objective coordination problems. We see a similar result here in the mining commodities problem. Here we don't have a log scale on the y-axis. So we weren't even able to run pmove on this problem. And cmove scales very poorly. This is our outer loop approach computing the true convex coverage set, and this is it computing epsilon coverage sets with different values of epsilon. So there are huge speed ups here due to taking an outer loop approach and tolerating some small error. So this is my last slide, and in this slide I just want to mention a few of the other directions. So what I've told you so far is actually just the tip of the iceberg. We've done quite a bit of other things related to this in our own research. So variable elimination is a computationally efficient algorithm, but it's not memory efficient. But we can take tree search algorithms that are memory efficient and use them instead of variable elimination in this linear support framework. And because linear support just solves a sequence of problems, its memory footprint is actually only as big as the memory footprint of the single objective solver. So we can directly obtain a memory efficient algorithm using this framework also. I think I'll skip this. So we've also successfully applied this framework to sequential decision problems, Markov decision processes, and partially observable Markov decision processes. And in doing so, the sort of key, the key to scalability, the key to being able to solve these problems in a tractable way is something that we call hot starting. So everything that I showed you here, when we solve the scalarized problem for a particular weight, we solve it from scratch. But that's actually not very smart, because in this linear support framework, chances are we've already solved a single objective problem for a similar weight. We have no guarantee that the solution will be the same, but if we hot start the solution for the new weight with the solution to the old weight, we can solve the problem for the new weight much more quickly. And this yields even bigger speed-ups, which is the key to success in the sequential decision-making setting. So I think I've talked long enough. Thank you very much for listening. I'd be happy to answer any more questions you have.
Okay, thanks so much, Shimon. Richard.
How should I think about it if I want to transform it into a kind of cost reduction style inverse rather than a maximization setting?
I mean, it's no problem. You can take your costs and multiply them by -1 and then maximize. It's no problem.
So just try once more. You know, search engines work fast because they do some pre-computation. I'm sure I shouldn't do this, but the message I'm getting is this is a type of pre-computation I can do to speed up some optimization problems.
Yeah.
But
yeah, I think that's
way more than that. I mean, I'm happy with that. That's good.
I think that's a totally fair characterization. I think of it as partial planning. You want to do some planning, but you don't really know the whole planning problem. Some key information about the planning problem is not available to you. So you're just going to do as much as you can in advance, so that later, when that information becomes available, implicitly or explicitly, then you're better off. That second stage is sped up by the first stage.
It's just currying.
Do in practice the first stages take a lot of time? I mean, do they take a single run of a single objective thingy? So in this outer loop thing you described, right? You make multiple runs of the sort of standard algorithm. Does each one take a week, or they all? If they're very quick, then you could just run it when you know the weights. Back to the question about whether you really need to stage this. And if they're slow, then it's really a lot of work.
So I find it difficult to give a general answer there because we have problems of all sizes. So in our experiments, we of course restrict our attention to problems where the single objective solution is not extremely expensive because we want the whole experiment to run in a week and not a year. But that's sort of, from the perspective of a scientist, we want that to be small so we can do our analysis. In the real world, of course, you have problems of all sizes. I think actually you answered your own question because if it's very expensive, then this is worth doing. If it's not expensive, then it's not worth doing. If you have a single objective planner that runs in real time.
In which it turns out to be worth doing.
Sorry?
Do you have applications in which it turns out to be worth doing?
Well, so it's easy to come up with applications for decision support. Because decision support simply requires you to have a human in the loop. These cost issues, these relative cost issues don't come up as directly. So all I need is some human for whom it is difficult to quantify the trade-offs between the preferences, and then I want to take this multi-objective approach and show them the convex coverage set.
Okay, so do you have humans who are finding this useful?
Yeah, absolutely. So I mean, we have a robotics project where we're doing this now, where we're trying to get the robot to behave in a socially intelligent way. We have different ways of learning cost functions from data. We need to integrate these cost functions so that at the end of the day, the robot has one policy according to which it behaves. How are we going to integrate these cost functions? There are a lot of idiosyncratic issues that we can't all capture in the planning problem and solve algorithmically. So what we want to do is say, okay, let's compute the coverage set, take each of these cost functions separately, compute the coverage set, and let's show it to the user. And in this case, the user is not the person interacting with the robot. The user is an engineer on our team who's going to look at the resulting behavior and say, yeah, this is the one that's about right. This is the policy that gives the right balance between the proxemic distance you stand from someone and whatever the other objectives are. So I think that definitely comes up in practice.
Okay, super. Well, we have drinks and time for further questions afterwards, so let's wrap it up in here and move outside. Thanks again, Shimon.
Thank you.